Okay, I think we'll get started. So today we're going to start the first of several lectures on chemical kinetics. So we've come off talking about physical kinetics and molecules colliding, and we know that for the most part, molecules have to collide to get a chemical reaction to happen. But now we want to talk about the actual monitoring of that chemical reaction such that we can talk about how fast the reaction happens. So kinetics is the area of chemistry that answers that question. Thermodynamics, which we've talked a bit about here, we'll talk about the equilibrium cases and we'll address will a reaction happen based on the delta G, but it won't say anything about how fast that reaction will happen. That's the realm of chemical kinetics. And so as a professional chemist, you need to know both things. So if you propose a molecule that you want to make, and you discover that thermodynamically it's very unfavorable, then it's going to be very hard to make. But if you discover that although it's thermodynamically favorable, it's very slow kinetics, then it may also be very hard to make. So these two areas come together for a professional chemist. Now in kinetics is very different than thermodynamics. In thermodynamics we can build the theory up with pencil and paper, and for equilibrium thermodynamics it's basically a solved science. It all swoops back to the three laws of thermodynamics, and so everything is rigorously well-founded. Kinetics is not that way at all. In fact, kinetics is very much an empirical science. So there are some theoretical ideas associated with kinetics, and there's people trying to make theoretical connections to the different various theories of chemistry, quantum mechanics, statistical mechanics, and thermodynamics. And in fact, we'll make some connections back to thermodynamics. But even there, that's forced a bit, and we utilize some of the ideas from these theories in areas that they really aren't valid for. But we get away with it, it works, and it sort of works. So essentially, kinetics is known to us via the several hundreds of years of fiddling around with chemistry and doing chemical reactions. And so we've built up this huge repertoire of reactions that we know about, reaction techniques, and ways to interrogate reactions. So today we're going to just talk a little bit about the overview of kinetics, get some important ideas down, and then in subsequent lectures we're going to talk about how to actually determine what are called the rate laws for kinetics. All right, so let's consider now an overall reaction. Now, what do we mean by overall? When we talk about an overall reaction, I want you to be thinking about the beaker level. We're going to mix these two solutions, and when we mix the two solutions, A moles of A are going to react with B moles of B to produce C moles of C and D moles of D. Do not think about this at the molecular level, thinking that A molecules of A collide with B molecules of B to produce C molecules of C and D molecules of D. That's likely not what's happening. When we write a reaction and talk about what we observe in the beaker, all we're seeing is where we start and where we finish. We're not seeing anything that might happen intermediately. So this could be A molecules of A, B molecules of B, all colliding at the same time and creating C molecules of C and D molecules of D. But it very much could be a series of reactions in which the intermediate products in those reactions don't hang around, they further react until we end up with C and D. And so we want to really very carefully distinguish this idea of an overall reaction. Now, we want to be able to follow this reaction to give an observed rate of the reaction. So we watch the reaction happen and we try to figure out how fast it's going. Now, by watch the reaction happen, we need to be able to key in on one of these species or perhaps have some kind of indicator in there. But let's for now just assume we've got this general reaction. Of course, this isn't completely general. I mean, we could have 100 reactants and 100 products or any number. But this is general enough for us to think about. And we're able to, let's say, monitor one of these. Let's say A has some color to it, and the rest are clear. So as the reaction proceeds, we can see that color fade away because A is being consumed. Or maybe D has some electrochemical activity, and we can monitor that and see that electrochemical activity increase as the reaction happens because D is coming in. We want to be able to define the rate of that reaction, or the reaction rate, reaction speed is sometimes called, reaction velocity sometimes it's called. And I've got a V here, and I've got a Greek letter nu here. It's very close. Try to keep those separate. We define the velocity as the rate of change. So a little calculus coming in here, but just think of this as a instantaneous rate of change of the species I with time. So how does it change? Little change in the species with a little change of time. Little change in the concentration. Now, we could just do that. But then, if I was monitoring A with the color and you were monitoring D with the electrochemistry, then we would get different velocities because, let's say A is 1 and little a is 1 and little d is 2, then for every A molecule that goes away, 2 D molecules are being produced. So we're producing D at twice the rate of A. So what we need to do to standardize that velocity so that we all measure the same velocity is to divide by the stoichiometric factor here. So nu is the stoichiometric factor with negative for reactants. So if it's on the reactant side, we put in a negative sign because that means it's going away. The derivative here is a negative number. So when we multiply by a negative, we get a positive reaction velocity. So 1 over A dA dt is equal to, if I'm doing this, then I will get the same result as you if you're doing this, 1 over D, d moles, or rate of change of D. All right, so this is what the rate is. It's this derivative, and that's pretty simple to write down. Now the idea of kinetics is that we try to figure out what's called the rate law. How does this derivative depend on the concentrations of the species present? Now, in the most general possible, to be as most general as possible, it would depend on all concentrations of every species present. Right? Also, it will depend on parameters. So these we'll consider these as the variables, the concentrations. There are many parameters like temperature, pressure, the solvent that's being used. But what we'll do is we'll assume that all stays constant during the reaction. We're only worried about the concentrations here as the independent variables. Now, a very large class of reactions don't have any feedback, meaning that the rate of the reaction is not dependent on the products that are formed, at least initially. Now, sometimes as the reaction proceeds, your rate law could change considerably. What we're usually looking for here is the early stages of the reaction, so that there's plenty of A to be around, but we're also forming some products. It can be that those products come back and influence the reaction rate in either a positive or negative feedback way. But a big portion do not have feedback. So we would not have a dependence on C and D here, and our rate law would simply be a function of the reactants. Now, in fact, there's also a subcategory of this that is very common. A very common type of reaction is what's called the power law. And in a typical general chemistry course, you would learn primarily the power law. In fact, in a typical physical chemistry course, advanced physical chemistry course, you would mostly be working with power laws. Only when you're really studying a course dedicated to kinetics would you worry about too much else. So very, very common reaction. And in a power law, we have a rate constant K. So the velocity is equal to a rate constant K. Now, this is constant with respect to what we're calling the independent variables here now, A and B. Not constant with respect to the solvent change, pressure, temperature, and so on. but we still call this a rate constant because we're wondering how is it dependent upon the concentrations, and it's just a constant of proportionality here. Then reactants raised to some power. Very important here. This is not the stoichiometry. So this n sub a and n sub b are not little a and little b here. So they could be quite different than little a and little b. And so that what that tells us, so the moral of this story, well, let me just say one more thing then. A and B are called the orders, and we would say that this reaction is n-8th order in A and n-bth order in B. So let me give a concrete example. So let's say this reaction up here was like this. We would say that this reaction is an overall third order. So it would be observed to be third order overall because it's first in B and second in A. All right. These don't have to be integers. We could, and they could even be 0. So we could have something like that, and then effectively B to the 0, which would just go away from the reaction. Okay, so we can have non-integers powers here. Usually they are integers though, at least for the types of reactions that we would run into in this introductory course. Okay, well, so I've been stressing a lot about this I've been stressing to you a lot about this overall reaction and thinking about that at the beaker level. Well, now we want to get down to that molecular level and think about molecules actually colliding. And if this were what we call an elementary reaction, then that really does mean A molecules of A collide with B molecules of B, all in one single collision to create D molecules of D and C molecules of C. So in one big collision, this reaction happens. And so as you think about it, the more we need to collide, the less likely that's probably going to be the case, right? So the very most common type of collision is a binary collision, just a collision between two molecules, then trinary, and so on. We can also have unitary collisions where where we might be colliding either with the wall or with an inert element. So there's that as well. Okay, so this brings up the idea of elementary reactions and the concept of molecularity. So for the case of an elementary reaction, because we are talking about the stoichiometry telling us what is happening at the molecular level, then the Na and the Nb really are the stoichiometric powers. So you can read those directly from the elementary reaction. So let's list unimolecular, bimolecular, and trimolecular reactions in terms of the molecularity. So unimolecular reactions. So this would be something like A goes to products and overall first order. So there's just a first order here and that's it. So V equals K, A to the first power. There are two types of bimolecular reactions. A plus B go to products, or A with A plus A, or 2A. In which case, again, the overall is 2 because it's bimolecular. So this means 2 here for the overall order. So Ka times B, each to the first order, or Ka to the second order. Reading directly from the stoichiometry here because these are elementary reactions. And let's do trinary, or trimolecular, sorry. So A, B, C, 2A plus B, and 3A. And we have the various rate laws, all overall third order. K times A times B times C for the first one, then Ka squared B for the second one, and then Ka cubed for the third one. All right, so let's see how the elementary reactions are related to an overall reaction, and that's called a mechanism for the overall reaction. We try to write the overall reaction in terms of a sequence of elementary reactions. So let's just for concreteness say we have this overall reaction. 2A plus B goes to C plus 2D. And we propose a mechanism. Now, that's a big portion of chemical kinetics, is to propose a mechanism. Synthetic chemists, those who make molecules, when they make their molecule, they want to ideally be able to tell the world how they think that molecule was made. That's very important because if you understand the mechanism, you might be able to tweak the reaction in a way that makes some sense, an educated guess on that tweak of the reaction to get a different product that you might be interested in, rather than just shooting in the dark. So let's say we propose a mechanism, a three-step mechanism. We say A and A react to form D and this A prime. A prime is what we call an intermediate. A prime then so this would be a bimolecular reaction because it's A with A, so that's bimolecular. Then A undergoes some kind of conformational change or something, unimolecular. And then we say that 2A plus B go to C and D. And that gives us finally the C and the D that we want, and the A and the B, the A and the B that we want. And we say this is trimolecular, let's say. So we have this reaction, and we've proposed this. Now, where we would be most open for criticism? Probably the trimolecular reaction. In that, in the trimolecular reaction, we need all three of these to come together and collide. Now, that certainly happens, and there certainly are mechanisms with trimolecular reactions. But if you can think of two bimolecular reactions instead of a trimolecular reaction, that's probably going to be the best mechanism to propose, because trimolecular reactions are much more rare than bimolecular reactions. Unimolecular reactions are kind of on a different scale. That's going to be involving just one molecule doing something, maybe a decomposition. And actually, I should have had this go into 2A. Let's say it decomposes into 2A here. Then I have a balanced reaction here. So yeah, maybe it decomposes, maybe it does a conformational change or something, and that can vary considerably in terms of how likely that is to happen. So it's a little harder to compare these with these, but always a bimolecular collision is much more common than a trimolecular collision. Now let's just say for the sake of an example, that this is the slow step. So we'll say that this step here is the one that takes a very long time. Then we say is this step is identified as what's called the rate determining step in this reaction. Now, how that plays itself out in the kinetics, the overall observed kinetics shouldn't have any of the intermediates in there because you aren't able to observe those. You know, maybe you can, but they aren't sitting there for a long time as stable reactants and products. So we have to have an overall rate law that involves the species present here. And let's say this is the rate determining step. If that's the case, then this is going to depend on the production of this guy, which will be very fast through here, but it leads itself back to just A. So once this goes, then this quickly goes. And again, we're thinking about the case when we're early on in the reaction. So there's plenty of A around, plenty of B around. We're starting to get plenty of C and D around, but we're still early in the reaction. The observed then would be only dependent on A, perhaps A squared. Right? Now this is an overall reaction, so it doesn't have to follow the stoichiometry here. And in fact, we would expect it here not to have any D or B, because this is fast and there was no B involved in getting to that fast step and getting hung up on this slow step. So this would be second order in A and 0th order in B. So here'd be an example of a case where we might expect to see a 0th order in B. Now, nothing can stay zeroth order forever. If this goes on and on, eventually we'll run out of B, and that'll start to slow the reaction down. But again, early in the reaction, if this is the slow step, then that's the rate determining step. There's no B involved, and so B would be zeroth order. Now, we can always disprove a elementary reaction. So if we have a mechanism, we say, I think this is an elementary reaction, we do some kinetics, and we get a rate law that does not jive with the stoichiometry, then we have proven that that is not an elementary reaction, because it must be the same as the stoichiometry. The order powers must be the same as the stoichiometric factors if it's an elementary reaction. Now, conversely, we can never prove a reaction is elementary. We can only support that idea. So we do a reaction, we think it's elementary, we get a rate law that matches the stoichiometry correctly, and so we say we've supported, now this experiment supports the idea that this is an elementary reaction. Okay, so there's a lopsidedness there. We can disprove something is elementary, but we cannot prove it. We can only support it is. There's a nice famous cautionary tale about this. If you look at the reaction dynamics of H2 plus I2 equals HI, very simple molecules, you might reasonably expect that upon a collision, the H bond breaks, the I bond breaks, forms HI. That would be a very reasonable thing to consider. You do an experiment, and if it's elementary, it would need to be first order in each of these, and it is. So you do an experiment that supports that idea. And then you say, okay, I think this is elementary. I've got strong support for it. It makes some sense. It's pretty simple molecules, and it's not unreasonable. But interestingly, if you take a different halogen, bromine, and look at this same reaction, you get a very complicated rate law. It's not even a power law. It even has a feedback. So the product is sitting here. So it's not even ones that we really talk about at this level. And so we see here that that is definitely then not elementary. So that does not disprove this is elementary. It now reduces a lot of the support that gave us. This supports the idea that it's elementary. We simply change iodine to bromine, which is a pretty straightforward change in how we're thinking about this, and yet now it's not elementary for sure. So that casts some doubts on our initial assumption that this was elementary. So there's a good example of the kind of things you have to think about in kinetics that you don't have to think about in more of these solved science or mathematically based, theoretically based sciences like thermodynamics. Okay, I just want to end with a few things here before we go on to the other lectures in the next days on actually how to get rate laws. That'll be the important thing there. So let's just talk a little bit about what the objectives of chemical kinetics are. So if you end up becoming a kineticist, you might be trying to establish empirical rate laws, determining overall mechanisms. That's a really important area. Empirical studies of elementary reactions, so really trying to understand these elementary reactions. Study chemical reaction dynamics, so looking at the dynamical behavior of products that are produced. This could include looking at angular momentum, vibrational dynamics that come off as these reactions happen, and then trying to establish theoretical links to the more rigorous theories of thermodynamics, statistical mechanics, and quantum mechanics. And the last thing here I want to talk about are how do we do kinetics when the reactions are on different timescales? So if we have a very slow reaction that might take hours or days to complete, then pretty much any technique that's reasonably fast will work. So if you have to take a little sample, bring it over to an instrument, make a measurement, and that takes 10 minutes or 5 minutes, 10 minutes, but the reaction takes 3 days to complete, then that time it took you to do that is inconsequential over the course of the reaction. So essentially that 10-minute period is like sampling an infinitely short period over that long 3-day reaction. So you have your leisure to choose any technique that works best for monitoring the reactants and products. Now, if it's a little bit faster so that the reaction is over, say, in 10 minutes, then certainly you couldn't do a reaction that takes 10 minutes because you take a little sample, it'd be reacting in that sample, and that reaction will have undergone a lot of its reaction during the course of the measurement. So there are two basic ideas here. We could continuously monitor. So you could actually do your reaction in the instrument that you're monitoring, or put some kind of probe in the reaction so that you can instantaneously be measuring, or very, very fast with a computer. Maybe every millisecond or something you are taking a measurement. So you can really pepper these 10 minutes of reaction. Another is a stop technique here, and that's kind of interesting. If the reaction is able to be stopped, so maybe it's driven by some compound, or you could throw another compound in and it just stops the reaction in its tracks, or it's an enzyme reaction, you kill the enzyme, or you plunge it into liquid nitrogen and slow the reaction down to basically a stop. These are called stopping techniques. And what you would do here is you would set up a sequence of reactions. Maybe imagine just 10 test tubes, and you start the reaction, start a stopwatch, and after 1 minute, maybe after 5 seconds, you stop this reaction, then 10 seconds, you stop this reaction, and so on and so on and so on. So you've stopped the reaction along the way, and then presumably then at your leisure with the stopped reactions, you're able to make your measurements that you would need. And finally, you come to these really fast reactions, seconds or subseconds. Then we have a problem because the reaction is over before it finishes mixing. So we have a mixing problem and we have a monitoring problem. And there's two things we can do here. On the mixing side of things, we can create what's called a cross-molecular beam. And so let me just sketch a picture of this. Let's call that A. So we create a beam of A molecules going in this direction, and a beam of B molecules going in this direction. And everywhere in here, there's no reaction because A and B aren't mixing. Everywhere in here, there's no reaction, but right here where the beams are crossing, and if these are going, nearly the speed of sound or ultrasound, then we have a very short time, and we can pinpoint precisely when these reacted. So as soon as they're out, as soon as the molecule is out of the reaction zone, then it's no longer reacting, and then presumably you make some kind of measurement on this. Now, these are very difficult. You're not making the same type of measurements, but you are able to gain some information about these fast reactions. Then finally, to monitor or even control, we can use ultra-fast spectroscopy. And so the famous example of that here is Ahmed Zewail's Nobel Prize for monitoring chemical reactions essentially in real time with ultra-fast spectroscopy. So we see the bond formation and breakage as it's happening. And so that's a really, of course, very interesting area of kinetics, but certainly quite different than in the slow reaction case where we might be using some of the more standard techniques. Right, so this is the idea of kinetics overview, and we now need to do the job of figuring out what the rate laws are. There's two ways to do it. One is called the method of initial rates, so we'll talk about that next time, and then integrated rate law, and we'll talk about that the time after that. The integrated rate law does involve some calculus, so we'll talk about that when we get to that case. For now, not a lot of homework for this. just read the sections in your chemistry book, whichever one you have, on kinetics to get yourself primed for this, and then think about some of these ideas, and then we'll get going with actually calculating or determining the rate law from experimental data.